Okay, so last Wednesday we started discussing the density matrix in the second hour. As some of you were absent and some of you don't remember studying the density matrix in quantum mechanics, I would like to just basically repeat what we had done, and then we will continue with the statistics. Okay, what do we do? You should be familiar with the wave function formalism. Of quantum mechanics. So where you basically have a wave function which satisfies a differential equation, where this psi is a function, h bar is a differential operator, and you are probably also familiar with the wave function with the matrix mechanics. So basically the equation can look almost identical, where now this h bar is a matrix and psi is a column vector. For example, if you study, I don't know, let's say the spin, the interaction of an electron with a magnetic field, okay, on one hand you have the differential operators, but the spin, the only way we can treat the spin is through matrices. So the Hamiltonian becomes a 2x2 matrix, the entries of which is itself a differential operator. Well, that's a possible formalism. Well, a third one, if you like, is the density matrix. So what do you calculate? Let's say that you find the wave function, let's say somehow. The quantities you are interested in are usually such objects, the expectation values. In Schrödinger picture, the wave function will be time dependent. The operator can be the position operator, the momentum operator, the energy operator, etc. The operators will be time independent, but I can write this exact same thing in a slightly different form. Let's say that I have a set of energy eigenstates of the Hamiltonian. They form a complete set. So I can write the identity operator as a sum over this complete set. If I insert, let's say, the identity operator over here, this expectation value can be written as sum over all these eigenstates of psi t, O, n, and psi of t. Which, let me just reorganize a bit. So is that this object over here is actually a matrix. So if you like, if you have a row matrix and a column matrix, a row matrix and a column matrix, if you multiply them in this form, this is just a number. But you can also multiply those two in this form. This will be an n by n matrix. This is like the bra. This is like the kit. No, sorry. This is the bra. This is the kit. So this is an operator. And that is an operator corresponding to what we call that operator we call the density matrix, rho of t. So if we know what rho of t is, this matrix element, this expectation value for the given system, can be written as sum over n rho of t N. This is nothing but the trace. There is also the O. Trace of rho of T times O. So if we know the density matrix, of course here in this derivation I derive the density matrix from the wave function, but if there are other means of evaluating the density matrix without referring to the wave function, if we know the density matrix, then I can calculate the expectation value. You can ask, what about the probability that my system will be in the state N? Well, if you look at that probability, that is psi of t, and this is my density matrix. Rho and n. So if I know the density matrix, if I choose a basis of eigenstates of the Hamiltonian, the nth diagonal entry just gives me the eigenvalue, the probability that my system will be in the nth state, or in fact, n can be anything. It doesn't even have to be an eigenstate of the Hamiltonian. Whatever n is, this matrix element, which is the diagonal element in the basis that contains this state n, gives me the probability that my system will be in the nth state. So what else do we calculate in quantum mechanics? We know the probabilities, we know the expectation values, so we can just use the wave function or the density matrix. Then I can ask the question, okay, what about the time dependence of this density matrix? That's also, that we will study in a moment. But then, of course, you should also ask if we can do the same thing as we, the same things that we do with wave function in terms of density matrix, what is the advantage of using the density matrix? So why don't we just stick with the wave function? Well, let's look at such systems. Let me say that I have a system A and system B somehow interacting with each other. This can be, for example, two spins or two electrons, or more complicated systems, a system and the heat reservoir. I can talk about the wave function of the whole system, A and B, which will be the sum of eigenstates of the AB system. Which in general, if A-B systems are separated enough, we can also write this as some eigenstates of the A system times the eigenstates of the B system. Sum over n and m. Now the question is, what is the wave function of the A system? If A system need not have its own wave function. I cannot write down a wave function of the A system. It's so-called entangled with the B system. I cannot separate them. Only in very special cases where this wave function of the whole system can be written as the product of wave functions of the A and the B system. Just if there is a single term in this expansion, only in that case I can talk about the wave function of the A system, but in general, well, the A system doesn't have its own wave function. It's just a combination of such products. So if I want to work with the wave functions, I have to know the wave function of the A and the B system, both of them. But usually I don't really care about the B system. What I would like to know is I would like to study the properties of the A system. Like, for example, I have an operator, let's say, which depends only on the degrees of freedom of the A system, the position and the momentum of the A system, particles making the A system only, let's say. And then, let's say I would like to calculate this expectation value. We have just seen that this is nothing but trace of the density matrix of the combined system times this operator. Well, the trace will be, let's say that, let me write this psi state as B and M, n of the A system times m of the B system. These two basically are the same, talking about the same thing. Now this trace would be let me put primes over here. This is what we mean by that trace. But you see, this OA only acts on the A system. So this is let me even first introduce an identity over there. KL. K are the quantum numbers of the A system, L are the quantum numbers of the B system. So this becomes summed over N prime, M prime, sum over K and L, N prime, M prime, rho AB, KL, K O A N prime L N prime B. Here I already used that the OA only acts on the wave function of the A system, not the B system. So that I could write this KL OA N prime M prime as K O A N prime L M prime. This is what I did. This is the A, this is the B. Well, this is if everything is properly normalized, etc. This is Kronecker delta L M prime. So already this is N prime M prime sum over K N prime M prime rho AB K L K A O A N prime A and L is equal to M prime, so this is M prime. Now, let me look at this quantity over here. N prime, M prime, rho AB, K, M prime, summed over M prime. M prime are the quantum numbers of the B system. So this is defined as the trace over the quantum numbers of the B system of rho AB. But then I still need to take the N prime K matrix element. Now this is what I will call rho of A. But keep in mind that this trace over B, rho AB, is actually summed over M prime rho AB, M prime. Let's, for example, look at it, the diagonal entry of this one. Well, see, this is the probability that my combined system is in the state Nm prime. I'm summing over all the possible states of the B system. So at the end of the day, what I obtain is the probability that my A system is in the N state, in the state N. So in that sense, this trace over B is still a kind of a density matrix whose diagonal entries gives me the probability distribution for my system. So let's go back over here. So let me take this one. This is sum over n prime k, n prime. Well, sum over n prime is what I will call row A, k, k, or A, n prime. Well, which is nothing but n prime row A, m prime, one is m. So where did I start? I started with, sum over n prime row A or A n prime. This is trace over the A degrees of freedom, row A. So what did we achieve? We start with the trace over the all the quantum numbers of the whole system. This trace, which is the expectation value of OA, this was actually equal to trace over only the A degrees of freedom, rho A or A, where this rho A is equal to trace over the B degrees of freedom of rho AB. Okay, so there is no way I can talk about the wave function of the A system, only except in certain special cases. But I can still talk about the density matrix of the A system without referring to the B system at all. Once I evaluate that trace, or as we will do here in statistical mechanics, we will know if the A system is in thermal equilibrium, we will know what the density matrix is, even if it's interacting with the reservoirs, the heat reservoir and the particle reservoir. So we cannot talk about the wave function of our system, but we can talk about the density matrix of the system. Yes?
Is any of these things a partial trace and a partial trace operator? Does any of these things know them, and what are they?
Yeah, so this is the partial trace.
Okay.
I'm taking a trace, but over only the degrees of freedom of the B system. How do I define that partial trace? This is the definition of the partial trace. Other questions? So we had already seen one property of the density matrix. Trace of rho A is equal to 1. Rho A squared, well, let's see what this rho A squared is. Well, let me just stick with a single system. There is no B system. So in that case, this is easy to evaluate. This is rho A. This is also rho A. This is 1, which is just rho A. So rho A squared is equal to rho A if and only if rho A can be written in this form. But you see, the density matrix doesn't have to be in that form. Let's say it might be possible that, let's say that we have a system of electrons. It is possible that we create these electrons such that 1/3 is in the spin-up state and 2/3 is in the spin-down state. This is also a possibility. You see, keep in mind that if you pick one, that is either spin up or spin down. If I have, I don't know, 30 electrons, 10 of them are prepared in spin up state, 20 of them are prepared in spin down state. So this is the corresponding density matrix. Let's calculate rho A squared. Now trace of rho A is 1. Is 1 over 3 plus 2 over 3. This is just 1. Now rho A squared will be equal to, well, let me just write it out first. Which will be 1 over 9 spin up, plus 4 over 9 spin down. There are no cross terms. Which is definitely not equal to rho A. So this property that rho A squared is equal to rho A, the square of the density matrix is equal to itself, it's not a general property. It is valid only if we can talk about the wave function of a system, only if there is a single wave function describing my system. But if you look at this example over here, there is no single wave function describing my system. So I can only talk about the probability that my system will be spin up and the probability that my system will be spin down. Note that rho A this is not equal to 1 over square root of 3 spin up plus square root of 2 over 3 spin down times 1 over square root of 3 spin up bra plus square root of 2 over 3 spin down bra. If I have such a system, I know that with 1/3 probability an electron I pick will be spin up, with 2/3 probability it will be spin down. It doesn't correspond to this wave function. If an electron has that particular wave function, with 1/3 probability I will measure its spin to be up, with 2/3 probability I will measure its spin down. Those are different things. So if you write the density matrix corresponding to the last one, this is 1/3 spin up, plus 2/3 spin down, plus square root of 2 over 3 spin down, spin up, plus square root of 2 over 3 spin up, spin down. There are different matrices. The probabilities I talk over here are not quantum mechanical probabilities. They're just classical probabilities. I just sum them up. Here, the quantum mechanical nature of the wave function is actually in these off-diagonal elements, which in a sense, in this density matrix, all those quantum mechanical interference effects are already gone.
Have we defined the pure atomic state yet?
Yes, your friend is already jumping ahead. You see, this is a pure state.
Right, that's the definition.
Yeah.
Okay.
It's a state which can be described by a wave function. Not every system can be described by a wave function. This is a mixed state. It cannot be described by a wave function. You see, since the diagonal entries, you see, rho kk, we said that this is the probability. Let's say that we find a basis where the density matrix is diagonal already. So rho will be rho 1, 1, rho 2, 2. All the others are 0. Rho squared will be rho 1, 1, rho, let's say kk squared, sum over all k, all the diagonal entries. You see, rho kk squared is less than or equal to rho kk, where equality holds only if and only if rho kk is equal to 0 or 1. Otherwise, rho kk squared cannot be equal to rho kk. Well, that means that this trace of rho squared. So trace of rho squared is less than or equal to sum over k rho kk, which is equal to 1. So trace of rho is equal to 1, but trace of rho squared is less than or equal to 1. How can we have equalities? Well, since the trace of rho is equal to 1, at most one of rho kk can be 1. Two diagonal entries cannot be 1. Only one of them can be 1. And if one of them is 1, all the rest should be 0. So trace of rho squared is equal to 1 only if rho can be written as all zeros except then 1, 1. But this means that if trace of rho squared is equal to 1, the system is in a pure state. And rho can be written as psi psi for some wave function psi. So if you know the density matrix, you can first test the trace of rho squared, and if you see that trace of rho squared is 1, you already know that when you diagonalize it, there will be only one non-zero entry along the diagonal, and you have a pure state. You can write down a wave function for your system corresponding to that density matrix. So if trace of rho squared is less than 1, then there's no hope of writing your wave function as a single state. There will be more than one entries along the diagonal, and none of them is the wave function, can be identified as the wave function of the system. So any questions up to here?
When you say rho squared up at the beginning, where you define the pure state?
Here.
I mean, no. Yes, here. So we say rho a squared equals rho a. But if that's the pure state, that squared could be an n. Any power of rho a can yield the same result. Why do we say that?
Well, I mean, if you have a matrix, especially if you have a large matrix, you would prefer to calculate the, I don't know, second power rather than the third or the fourth or the fifth powers. And furthermore, you can have, for example, rho a to the fourth power is equal to rho a, but rho a squared could have been minus 1. Not for a density matrix, but in general for matrices, I mean, rho a squared is equal to rho a is more strict than saying that rho a cubed is equal to rho a. Other questions? Okay, so in general, the density matrix of a given system will be sum over whatever wave function it can have, whatever state it can be in, the probability that my system will be in the kth is prepared in the kth state times psi k, psi k. If the wave functions are time dependent, rho itself will be time dependent. You see, you know Schrödinger's picture. And there's also the Heisenberg picture. Well, in the Schrödinger picture, states are time dependent, In the Heisenberg picture, they are time independent. Operators, of course, assuming they don't have explicit time dependence, operators that are made up of like position and momentum, in the Schrödinger picture, they are time independent. For example, expectation value of the position of a particle changes in the Schrödinger picture, not because the position operator depends on time, but its expectation value depends on time because the wave function is time dependent. Whereas in the Heisenberg picture, the operators are time dependent. In the Heisenberg picture, states don't change, the position operator itself changes in time. Density matrix is an exception, let's say. In the Schrödinger picture, it is time dependent. Basically, it replaces the wave function. Since wave function is time dependent in Schrödinger picture, so is the density matrix. In Heisenberg picture, it is time independent. So let's look at the time dependence of the density matrix. I'm just using the chain rule for products. Okay, what's the time derivative of the bra? In Heisenberg picture, what's the time derivative?
Zero. Heisenberg picture, what are we asking?
Schrödinger picture. What's the time derivative of this bra? Yeah, remember, h psi is I h bar del over del t psi. So this is 1 over I h bar h psi k of t plus psi k of t h psi k of t, but I have to have h dagger, and there is this I, so this is a minus sign. Well, h dagger is h, so this is just 1 over I h bar, h acting on this operator from the left minus that operator multiplied with h from the right. But this is nothing but rho. So the time derivative of rho is 1 over I h bar, the commutator of h with rho. Now this is the equivalent of the Liouville theorem for the density matrix. Now what are these PKs? Oh, okay, so let me, okay. So any questions up to here? See, in the end, what we will obtain is basically our conclusion would be whatever we had used before, we are justified to continue using the same approach in quantum mechanical systems. So this already tells me that in equilibrium, you see, this is general. That if you have any system, whether it's interacting with the environment or not, I don't really care, the density matrix corresponding to that system, its time derivative is given by the commutator of the density matrix with the Hamiltonian of the system. In equilibrium, well, nothing changes with time. So the Hamiltonian should commute with rho. Well, this was basically we also had in Liouville's theorem the Poisson bracket of the Hamiltonian with the density of state density in the phase space had to be 0. So then it has to be a conserved quantity, let's say rho. Well, the same thing holds over here. Rho has to commute with H. Now, what is the ensemble theory here? We have already started doing the ensembles. You see, what do we do in the ensembles? We just make copies of the same system. Many copies. Well, there will be a finite, if you pick one randomly, there will be a finite probability that it will be in the state psi k. So these are the probabilities of the state psi k. So this summation over k is actually kind of a summation over the copies in the ensemble. So if we want to calculate the average of any quantity, this will be equal to trace of rho of t O, which will be trace of pk psi k of t, t of k, O. This will be sum over k, psi k of t, O, psi k of t. Okay, one thing you should pay attention here. This is quantum mechanical averaging or expectation value. This is ensemble averaging. Or expectation value. So we have, in a sense, we have two kind of expectation values here, or the averaging we will be performing. One on the quantum mechanical state that my system can be in, and the other one over the ensemble. Now, of course, so what is rho? Now, we had these three different ensembles. Basically, we have the same things over here. There is a microcanonical ensemble. Which says that rho n m is equal to rho n Kronecker delta n m, and rho n is equal to 1 over gamma if n is an accessible state and 0 otherwise. Well, if you remember what we had done in the classical description in the microcanonical ensemble, what we had started was, okay, so we said that, okay, the system is constrained in energy, the number is also constrained, the number is already fixed. The energy is also fixed, we are looking at an isolated system. So these, if you look at an n-particle phase space, this constraint of energy, that the total energy is given by E, just defines the hypersurface, and we assume that the probability that the system will be in any one of those points in this hypersurface will be equal to each other. There will be a uniform probability. Well, this is the quantum mechanical expression of basically the same thing. So if this n corresponds to an accessible state, then they will all have the same probability. Otherwise, okay, my system cannot go there anyway. Now, what is this rho nm? Or we said that pk and psi k m. Let's see what it will look like in a different basis. I will be just making a change of state. So I will be interested in, let's say, rho prime, n prime, m prime, which is I will define as n prime rho m prime. I don't necessarily have to use the energy basis. Why should I? I'm just changing to a different basis. The rho density matrix is still the same. It will just look different. This is the, let's say, the operator form of the density matrix. So this will be given by, let me see. Now I would like to relate this somehow to rho nm. So I will insert identities. So here I will insert this identity, here I will insert this identity. So this will be equal to sum over n and m, n prime n, rho n m, m prime. Again, it's just a change of basis. Let me say that, let me already use the fact that rho was diagonal in the microcanonical ensemble. So let me write Kronecker delta n m rho n, which will be n m n prime n m n m prime rho n. Do you see a problem? It's no longer diagonal, unless we make additional assumptions. You see here, I'm basically assuming that rho is proportional to the identity matrix. Identity matrix doesn't change in a change of basis. But since it's the density matrix, it has to satisfy certain properties, blah, blah. But now in a different basis, this is how it looks like. Well, of course, if you say that rho n is a constant, I can take it out of the summation sign. This is just rho. Yeah. This will be equal to, let's say, rho 0. There's no summation over m here. N prime, n m prime. Well, this is rho 0, n prime, m prime, rho 0, Kronecker delta n prime, m prime. Okay, so it's still diagonal. For this special case of rho being a constant. But I would rather keep it diagonal in any base. In that case, rho n will not be a constant. This basically tells me that I cannot make it diagonal in every basis, unless I make an approximation, an assumption. You see, what is this? Let me write it in this form. Phi n and phi m prime are nothing but the phases of these quantities. But you see, these phi n's and phi m n primes and m primes, they will be mainly arbitrary. not arbitrary, but they will be fluctuating. They will be changing as I change n and m, n and as I change n, phi n prime and phi n prime will be changing. So what we often do is what's called the random phase approximation. You see, unless n prime and m prime are equal, you see, if n prime and m prime are equal, there's no phase. There's no random phase. So everything here is a positive number. So rho n prime is definitely a positive number. But if n prime and m prime are different, then in general those phases will be different. And as I change n, the phases will also change. But the phases will be positive, negative in different directions, and I'm summing over all these phases. I will assume that all these numbers cancel each other. So this random phase approximation is essentially sum over n prime and m prime rho n e to power I phi n prime minus phi m prime is equal to 0 if n prime is not equal to m prime. Why is it 0? Because of those phases. And they will just make sure that this numbers that I'm summing over, if you imagine the complex plane, they will be all pointing in different directions in the complex plane. And so when I sum them up, it's not just the summation, a coherent sum, it's just a random sum. Some of them will be pointing in this direction, the other one will be pointing in this direction, other one will be pointing in that direction. So the sum is assumed to be 0. Of course, this can only be assumed if n prime and m prime are different than 0. So with this random phase approximation, I can say that rho n m, okay, with random phase approximation is diagonal in any basis. Whatever the diagonal, whatever the values of the diagonal entries are. So whichever basis you use, row matrix becomes diagonal, basically. Unless you prepare your state in a special way. For example, a pure state is a special kind of state. You have to work really hard to create a system in a pure state. Unless you make such preparations, let's say, the off-diagonal entries in any basis of the density matrix will be 0 or negligible compared to the diagonal entries. The diagonal entries will be non-negligible, mainly because they are the probabilities that your system will be in particular states or not. So any questions up to here? So let's give our break now, and we will continue in 10 minutes.